In this next set of lectures, we're going to talk about principal component analysis, which is a method to analyze multivariate data. And we're going to talk about multivariate data in a minute. Principal component analysis is also known as PCA, which is the acronym, which you'll hear more. So we're going to start with understanding what is multivariate analysis. We're going to explain some of the mathematical basis of a PCA. Now that you have kind of linear algebra a little bit under your belt, you can understand vectors and how we can rotate data in a multidimensional space. And then we're going to apply a PCA to data in R because unlike the mathematical basis, which is really hard to understand, in this case the application of a PCA is actually quite simple. And of course, interpreting the results from a PCA is critical, and we're going to cover that in detail. So until now, we kept thinking of a variable as this one response variable. So we have dt to dt, one temperature, a slope of one variable of temperature over certain conditions. And that is what we call a univariate analysis, one variable. So we can have, we have many predictors, you know, I mean, like I can talk about tree growth as a function of water and sunshine. I can add all the things and nutrient levels, but really I'm measuring tree growth. So my response data is a scalar. I have one response variable. And in multivariate analysis this time, which is a bit more realistic, I'm measuring more than one response variable at a time. I still could have many predictors, but I'm measuring more than one thing. So if at a certain site I'm measuring daily temperature, I'm measuring the maximum temperature, I'm measuring the minimum temperature, I'm measuring all these things, and I don't want to lose that information. So this time I have multivariate analysis, and I want to create an analysis that can take all of those responses into account. So this time our response data is a vector, okay, which is why we waited till this point to talk about it, because now you know that a vector has more than one dimension. So if previously all my responses were scalar, now I have a response that is responding as a vector. So I'll give you some examples. So for each time point or for each dx, we collect multiple measurements of data, multiple dimensions. Okay, so if we think about each one as a dimension on an x, so if we have x, y, we have two dimensionals. X, Y, Z, we have three dimensionals. I mean, like we can have many, many dimensions now. We obviously cannot plot it. And we call this multivariate. An example would be I took a sample of plankton from the ocean, and I'm counting at each depth all sorts of different species. Okay, so every depth has many response variables. I can look at copepods. I can look at, the assemblage of species in my data. And in order to explain how PCA works, I'm going to give you an example. And I'm going to get you to imagine a spring, like the ones you used to do at school when you were studying physics. And there's a red ball on the end of it, okay? We're going to assume no friction. We don't have to care about the friction in this case. So we have some sort of ball position, okay? So you've loaded the spring with the ball and you pulled it, and now it's going, say, up and down. And my ball position is a function of time, right? Because at each time point, it depends on the spring constant, right? And the displacement. And you don't have to remember this, okay? K is the spring constant and everything. All that you need to know is that at different time points, the ball is at different locations because it is spring. And I can predict it because it's a simple function of time. So the ball is moving along the x-axis, this displacement axis. My problem is when it starts with, I don't know where is the x. I don't have that a priori knowledge of knowing where to look. I don't know where the ball is moving. Imagine I can't see this yet. The ball is moving along the x-axis. I don't know what x-axis is, but I can try to look from different angles. And from that, I'm going to work out what the x-axis is. So here's the ball motion, and I'm going to have my looking is going to be different cameras. I'm going to have camera A, camera B, camera C. Really, if I wanted to see this ball going up and down with the spring along the x-axis, where do I need to put my camera? Looking this way. A camera looking from here is not going to see any motion at all, right? Because we have this ball motion, which is a simple spring kinetics, and I can work out the function if I know to look from x. But I haven't looked from x because I don't know where x is. I'm looking from here, from A, B, and C. And from A, B, and C, I'm generating a set of coordinates, right? Okay, so from B, I have this basis. From any camera here, I'm going to have this basis. So I'm going to watch the spring move along these two axes. Okay, and I want to get from this complex set of equations, okay, so from the displacement along this basis, from this x, y, bx, by, from this one, I want to actually collapse that and simplify it to get a simple equation of the ball movement along x, okay, because all of these have some sort of x component in them. So if I look through the time points, okay, and I'm looking from camera C, I'm going to see this is the xy of camera C, of that basis, not this one. This is my imaginary one that I'm trying to put together. I'm going to see the ball appear sometimes, disappear at others. I'm not going to see that big movement going up and down, okay? Sometimes I'm going to see this red ball. But that's enough information. If I have enough points of view, I can take this information and reduce it. So I'm back into a two-dimensional vector, but from the right direction of view. So I can rotate these cameras so that I can take the information in them and rotate and generate a fake, or not fake, a true x-axis that I haven't actually measured. So for each m measurements, okay, every time sample is a vector in an m-dimensional field. And here I have 3 fields, okay, so 3 measurements. I have many fields, and all the measurements in this field are a linear combination of the unit vectors, right? Remember the unit vectors, and we can combine them linearly. So principal component analysis is actually one of the most valuable results of linear algebra that you've learned, and it's used extensively in a diversity of fields. I've given you quite a few examples already, and the point of it is to simplify complex data. So at each depth, I've measured plankton, and there are like 50 different species. What do I do with that kind of information? How can I use that? So I need to simplify it to something different that has less dimensions and that I can work with. And it is a mathematically simple story. It's not simple for us, given we're not mathematicians, but it is simple linear algebra. So in the next video, we're going to start talking about